Have you ever stopped to think about sound? I mean, really think about it? It's everywhere all the time, but what is it exactly? Well, today we're going to dive deep and unpack the science behind something we pretty much take for granted every single day. Okay, let's kick things off with a classic. You've been there, right? A big storm is rolling in. You see this massive, brilliant flash of lightning that just lights up the whole sky. And then you wait. You start counting. 1, 2, 3. And then, boom! The thunder finally hits. So what's with the delay? Why don't they happen at the same time? The answer to that question is all tangled up in the physics of sound, and that's exactly what we're going to unravel. So to get to the bottom of that whole lightning and thunder thing, we've got to back up a little. We need to start with the most fundamental question of all. What even is sound? Okay, so at its most basic level, sound is just energy. That's it. It's energy that gets created anytime something vibrates. Think about it. A guitar string getting plucked, your own vocal cords humming, or yeah, a huge clap of thunder. All those things are vibrating, and those vibrations pump out energy. And it's that energy that our ears and brain interpret as sound. But here's the catch, and it's a really important one. That energy can't just travel through empty space. It needs something to travel through. It needs a medium, a solid, a liquid, or a gas. This is the absolute golden rule of sound. And it's exactly why you see all those silent explosions in sci-fi movies set in space. In a vacuum, there's nothing, no particles for the vibration to travel on. So no particles, no sound. Simple as that. All right, so we've got vibrational energy moving through a medium. Check. But how does it actually do that? Well, it travels in the form of waves. So let's get into it and dissect a sound wave. First up, we've got amplitude. The easiest way to think about this is just the size or the power of the wave. If a wave has a really high amplitude, it's packing a lot of energy, and our brain hears that as a really loud sound. And if it's got a low amplitude, well, you guessed it, it's just a quiet sound. Okay, next on the list is frequency. This one's all about speed, specifically how many vibrations are happening every single second. We measure this in something called hertz, or Hz. And what frequency really controls is the pitch of the sound. So if you have a ton of vibrations crammed into 1 second, that's a high frequency, and you get a high-pitched sound, like a whistle. On the flip side, fewer vibrations mean a low frequency, and that gives you a deep, low sound like a bass drum. And last but not least, we have wavelength. This is literally just the physical distance from the top of one wave to the top of the next one. And it's directly related to frequency, right? High-frequency sounds, where the waves are all squished together, have a super short wavelength. And those low-frequency sounds, they're all stretched out, so they have a really long wavelength. Makes sense. So the really cool part is how all three of these things are totally connected. In fact, there's a simple formula for it. The speed of a wave, or its velocity, is just its frequency multiplied by its wavelength. How fast it vibrates times how far apart the waves are. That simple relationship is what gives us the speed of sound. Okay, so now we know what a sound wave is made of. We get the blueprint. So let's put it on the clock. How fast does this thing actually travel? And here's a key question. Is it always the same speed? And the answer is, it totally depends. The medium it's traveling through is a massive game changer. Look at this. In air, sound kind of cruises along at about 330 meters per second. But put it in water, it's suddenly going over 4 times faster. And in a solid like steel, it's just mind-blowing. We're talking 5,100 meters per second. So why the huge difference? Well, it's all about how tightly packed the particles are. In steel, they're right next to each other, so they can pass that vibration energy along super, super fast. And wow, this chart really puts it into perspective, doesn't it? I mean, look at that little bar for air compared to the absolute skyscraper for steel. It's not even a competition. Sound is an absolute speed demon when it's moving through solids, all because those particles are jammed so close together that they pass the vibration along almost instantly. Okay, so we've got a good handle on the speed of sound. But now, it's time for the main event, the ultimate showdown. Sound versus light. And folks, I've got to tell you, this isn't even a fair fight. Sound in air is kind of just jogging along at 330 meters per second. Meanwhile, light is moving at, get this, nearly 300 million meters per second. That's just, it's almost impossible to wrap your head around that kind of speed. And right there, that's it. That is the answer to our very first question. The light from that lightning flash, it travels so ridiculously fast that it reaches your eyes pretty much instantly. The journey is over in a blink.
But the sound, the thunder, it's just chugging along at its 330 meters per second, so it takes a few seconds to make the same trip. Light wins. It wins the race to your eyes every single time. All right, mystery solved, but the story of sound doesn't stop there. Not even close. The world of sound is actually way, way bigger than what we can personally hear. There's this whole invisible spectrum of sound all around us all the time that we're completely oblivious to. It turns out our hearing is, well, it's kind of limited. We can generally hear frequencies between about 20 hertz and 20,000 hertz. Anything lower than that is called infrasonic. We're talking about the super deep rumbles from things like earthquakes. And anything above 20,000 hertz, that's ultrasonic. We can't hear it at all, but a lot of animals, like bats and dolphins, basically live and communicate in that high-frequency world.
Now, just because we can't hear these ultrasonic frequencies doesn't mean they're not incredibly powerful. In fact, humans have figured out how to harness these invisible sound waves, and it's given us some pretty amazing, almost science fiction-like superpowers.
I mean, just think about what we can do with it. We can use it to see where light can't reach, like using sonar to map out the entire ocean floor. In medicine, we use it for ultrasounds to safely see inside the body to look at organs and check on unborn babies. Industrially, it can spot tiny, invisible cracks in metal or clean delicate parts with incredible precision. It can even be used in surgery to blast kidney stones to dust without ever making a cut. It is, without a doubt, a true hidden superpower. So look how far we've come. We started with the simple question about a thunderstorm, and we ended up in this incredible world of invisible forces that let us navigate the deepest oceans and literally see inside our own bodies. It just goes to show you, sound is so much more than just noise. It's this fundamental, powerful form of energy that we're still just scratching the surface of. Which leaves me with one final question for you. What will we learn to see with it next?